Good afternoon, good evening, good morning, whenever you're watching this. This is topic 7.9 for AP Chemistry. Introduction to Le Chatelier's principle. The objective today is to be able to identify the response of a system at equilibrium in response to an external stress, whatever that may be. So some external pressures could be maybe change in temperature, change in pressure, change in volume, and then you have to make sure you know how the reaction will respond since it's at equilibrium. So the Chatelier's principle states that a system at equilibrium will most likely stay at equilibrium when some type of stress, story of my life, is applied. In other words, when a stress, so temperature, pressure, concentration, sorry about that, the reaction will try to respond in a way to minimize the effects of said stress. So the equilibrium constant for a reaction is mathematically determined. You have your concentration or your partial pressure of your products, and these are all raised to their stoichiometric coefficients, and then you divide that by the concentration of the reactants, and those also raised by their coefficients. So here's an example here. So you should know how to read that, interpret that, etc. So as long as the temperature is unchanged, the equilibrium constant should remain the same. So just remind, only thing that will change the equilibrium constant, the K value, is going to be temperature. So if some reactant A is added, the concentration of A is increased. That will disturb the equilibrium. And in order to reestablish that equilibrium, it's going to shift. It will shift to favor the reaction so that it uses up the A, so it's going to go forward. So the idea is that if you add more reactant, the reaction will move forward to kind of get rid of it to create more product. Okay. If you have more product the concentration of product is increased, it's going to go in the reverse direction in order to kind of use up that added product. Okay. So increasing whenever you add a reactant or a product, the reaction will shift towards the opposite side, therefore driving it in that direction. So, sorry, the exact opposite. So by removing a reactant or a product or decreasing the concentration of something will cause the reaction to shift towards that direction. So for example, if you get rid of some reactant, maybe you decrease the amount of something, I don't know, I can't think of anything right now. But it will cause a reaction to go towards that to kind of create that that thing that you took away from it. So talking about gases and pressures, changes in pressure also can cause a shift in the reaction. So if I increase pressure on the system by maybe decreasing the volume, the system will try to alleviate that stress, and it's going to go by shifting towards the side of the reaction with fewer moles of gas. So hopefully your reaction is balanced correctly, that you balance it correctly, or it's given to you balanced. So if you increase the pressure, story of my life too, if you increase that, you are going to shift the reaction towards the side of the reaction that will have the lower amount of moles. If you increase the volume, this will decrease the pressure. If the reaction is at equilibrium and your volume of the container increases, the pressure would decrease. It's the opposite, right? The system would counteract by shifting towards the reactants, creating more moles of gas. So if you increase the volume, you're going to shift towards the side that has more moles, essentially. If you add an inert gas, so maybe some type of noble gas potentially, you'll have no effect, and both sides of the reaction remain the same or at equivalent partial pressures. So changing the temperature is the final way to kind of apply stress. If you heat your reaction, your reverse reaction is favored, producing more of the reactants and consuming of the products. Increasing the temperature, you're kind of adding a product. So the reaction will shift to the left. By decreasing the temperature, you're causing the reaction to shift to the right in order to replace the energy that was removed. So if you're cooling a reaction, more products are formed, thereby consuming the reactants. So the way to look at heating or cooling is by looking it as adding or removing a reactant or a product. So it depends if the reaction is going to be exothermic or endothermic. If you're heating it up, you're causing the reaction to shift away from heat in the reaction, and cooling would shift the reaction towards heat in the reaction. Since your ratio of reactants and products is therefore altered by the changes in temperature, that's why your K value will change. Adding a catalyst will not stress the system. So if you do add a catalyst, though, you are decreasing the activation energies both forwards and reverse, so therefore it'll make the reaction reach equilibrium faster. But you're not changing equilibrium. You're just going to get there quicker. In an endothermic process, phosgene gas decomposes into carbon monoxide gas and chlorine gas. The value, if you will, is 0.0071. Using Le Chatelier's principle, predict how the reaction will respond to the following stressors. So first one, I'm adding more phosgene gas. The second one, I'm removing CO, carbon monoxide. I'm increasing the pressure and decreasing the temperature. So what I'm doing here is I'm adding a reactant. So this will cause the reaction to move towards the product. So it's going to shift to the right. Since I'm adding a reactant, the reaction will shift to the right. Removing CO, so I'm removing a product, would cause the reaction to move toward the product, so it's going to shift to the right. Removing a product drives the forward reaction. It shifts to the right. Increasing the pressure. Increasing the pressure would cause this reaction to shift towards the side with the least amount or the lower amount of moles of gas. So the system tries to alleviate the stress, so you are going to shift to the left, because on the left side of my double-sided arrow, I have 1 mole of gas in comparison to the 2 moles of gas on the other side. So increasing the pressure shifts the reaction to the side with fewer moles of gas, so this shifts towards the left. So I'm going to erase these. So give you a chance to write this down, etc. Blah, blah. If you need to pause it or rehear this, you can. So it's going to reiterate really quick. Adding more COCl2, since I'm adding a reactant, the forward reaction will occur. Therefore, it shifts to the right. Removing a product drives the forward reaction. It shifts to the right. Increasing the pressure shifts the reaction to the side with fewer moles of gas. So this reaction shifts towards the left in an attempt to alleviate stress. Oops. There we go. Okay, so decreasing the temperature, what will that do? Decreasing the temperature, what will that do? Since this reaction is endothermic, it tells us in the problem, energy acts as a reactant. So it takes in energy to form the products type of thing. So by decreasing the temperature, you're essentially decreasing the concentration of reactant. So therefore it's going to shift to the left. So I'm going to I need more space for this. Since this reaction is endothermic, energy acts as a reactant. Decreasing the temperature decreases a reactant. Therefore, the reverse. I'll try. Therefore, the reaction shifts to the products. To the products. Sorry about that. To the reactants. It's my bad. To the reactants. Consider the reaction known as the Haber process. So we have nitrogen gas plus 3 moles of hydrogen gas producing 2 moles of ammonia. It is determined that increasing the temperature causes the equilibrium to shift towards the products. Does this mean the reaction is endo or exothermic? So I'm going to give you a chance to think about it. And maybe think what you think the proper answer will probably be, and we'll go from there. So, is this endo or exothermic? So we're shifting towards the products. That means this reaction is driven towards the product side. Therefore, we have to think of this reaction as endothermic. Since we're adding heat to this, like endothermic means heat is being absorbed, it is producing more product. So by increasing a reactant, increasing heat, we are causing this reaction, this forward reaction to occur. Therefore, because of the shift towards the products, this must be endothermic. If the reaction is at equilibrium and the pressure is increased, what direction will the equilibrium shift? Okay, so if I'm increasing pressure, like we talked about earlier, but the reaction will shift towards the side with the lesser amount of moles of gas. Therefore, this will shift towards the product side. Just some things to think about. Letter C. The Haber process is used to create ammonia as an industry standard. In order to create the largest amount of product possible, they allow the reaction to come to equilibrium and then cool the reaction quickly. Use your knowledge of IMFs to explain why this is deemed the best way to proceed with the reaction. So, this is going to take some time, I guess, to answer this one. But it's actually a really cool process once we talk about this. So I don't have much space. Probably should create another slide, but it's fine. So I'm going to verbalize it. You need to pay attention, okay? So as the temperature decreases, the molecules of ammonia formed, they will condense and form a liquid. It makes sense because you're decreasing the temperature. So it's cooling it. So in doing so think about this. Think about the LDFs in H2 and N2. Because of the LDFs within H2 and N2, this will cause them to remain as gases when the temperature is cooled, but NH3 is now a liquid, and in doing so, this eliminates the ammonia from the equilibrium expression, so to speak. By removing it from the reaction, now there's an absence of ammonia. Therefore, the reaction will have to move forward in order to produce more product and to maintain that equilibrium. The process goes all over again since there's no more gaseous ammonia, no more NH3. So I think that's pretty cool. So essentially, to summarize letter C, using our knowledge of IMFs. So as the temperature decreases, the molecules of NH3 will be condensed and form a liquid. So regarding the LDFs at H2 and N2, think about the LDFs present there versus the LDFs present in ammonia. So what kind are they again? So now at this temperature, NH3 is a liquid, but by only having gaseous H2 and N2, ammonia is eliminated, the gas, if you will. So therefore, the reaction has to shift forward to produce more gas, produce more ammonia. Hence why it's really effective. So if you have any questions, please let me know. Thanks.